Today's lesson is on solving exponential and log functions. To start, we're going to review solving a couple of exponential functions, which we've already touched upon when we first started logs, but these ones are going to be a little bit more challenging to do. So when you're solving for exponential equations, you have to get the exponential expression by itself. So we need to isolate 2 to the power of x plus 6. But by doing that, or to do that, we need to add 4 to both sides. 2 to the power of x plus 6 is equal to 28. I'm sorry, 32. Now, the only way to solve an exponential function like this is to create common bases. So I need to create a common base between the left and right side, and that common base is going to be 2. 2 to the power of x plus 6 will remain. 32 is going to be rewritten as 2 to the power of 5. Once the bases are the same, then you can set the exponents equal. So I can set x plus 6 equal to 5 in order to solve for this. Subtract 6 from both sides, x is equal to -1. And that's the solution. Of course, you can check your work by substituting that back into the original function and making sure the function comes out to be true. We're going to follow the same process for number 2. We have 30 is equal to 3 plus 9 raised to the power of 2x minus 5. I'm going to start off by subtracting 3 from both sides. 27 is equal to 9 raised to the power of 2x minus 5. I can rewrite 27 as 3 cubed. And I can rewrite 9 as 3 squared. The value of 9 already had an exponent. It was 2x minus 5. When you have the power property for exponents, you need to multiply them together. 3 cubed is equal to, when you multiply, make sure you distribute your value. This is equal to 3 raised to the power of 4x minus 10. At this point, our bases are the same, so we can set our exponents equal. In order to solve, I'll add 10 to both sides, and then I divide both sides by 4, giving me a solution of 13 over 4 for my final answer. And you can check that, make sure it comes out to be true. So now we're going to work towards solving log equations. There are 2 types of log equations that we're going to be looking at. The first type is when you have a logarithm only on one side. If you look at my example right here, it's log base b of x is equal to y. That means there is only a log on the left side of the equal sign. It could technically be on both sides, but in this case it's on, it could technically be on either side. In this case, it's on the left. So right here it says if you have a single logarithm on one side of the equation, then you can express it as an exponential equation and solve. An example of a problem like this could be something such as the ones we've already done. Log base 2 of 8 is equal to y. In order to solve for this, you would convert this to 2 to the power of y is equal to 8, and then you would solve for y. Sometimes you're going to have to apply logarithm properties, meaning you'll have to apply the quotient or product property in order to use this type. But type 1, just to recap, is when a log is on only one side of the equal sign. And that brings us to type 2. Type 2 is when you have a logarithm on both sides of the equal sign. If that's the case, and your base is exactly the same on both sides, then you can just set the arguments equal to one another. So same thing goes here. You might have to use log properties in order to simplify. But an example could be log base 4 of x is equal to log base 4 of 16. Because the log and the base are the same on each side of the equal sign, we can go ahead and say that the arguments are equal, or x is equal to 16. I do have a couple of notes down here for you. On this side, it says equations having multiple log expressions may be solved by first condensing expressions using the power, product, and quotient properties, which is what we went over yesterday. So sometimes you have to apply those before you can solve. And then here it says it is okay to have values of x such as positive values, 0, and negative numbers. However, it is not okay to have a log of a negative number or a 0 when it's evaluated. So there's two important ones to see. We're looking at the log of a negative number is undefined, and the log of 0 is also undefined. So those two are important to recognize in case you see them anywhere. You can never have a negative argument. That note is telling you that the value of x could be negative because maybe you're adding a larger number to it. So don't just assume if x is negative, then the argument is actually negative. The whole argument has to be negative. Okay, moving into the first example set. So I did type up here for you saying that it's type 1, which means there's only a log on one side of the equal sign. However, most of the time I will not specifically say which type that you need to use. You need to recognize, is there a log on one side or is there a log on both sides of the equal sign? Looking at number 1, we have log base 8 of x cubed. This is equal to 12. In order to solve, we need to isolate the logarithm. We need to get the log and the base by itself. I do recognize that I have that exponent. It will be helpful to write the exponent in front as 3 times log base 8 of x is equal to 12, because doing this allows us to divide out that value. So now I can move the value of 3 easily to the other side, and that's something that will happen all the time. Log base 8 of x is equal to 12 divided by 3, which is 4. Once you get the log as simple as possible, so once you isolate this as much as you can, you want to convert to exponential form and then solve. Converting to exponential form is going to give me 8 to the power of 4 is equal to x. And now this just becomes something you either need to calculate out or type into your calculator, but 8 to the power of 4 is 4,096. That is your solution. So to add a couple notes in there for you, you want to simplify as much as possible. And once you simplify as much as possible, you want to convert to exponential form and solve. Number 2, 6 plus 2 times log, this would be base 10 of 5x is equal to 18. Don't forget the common logarithm is always base 10. We need to isolate the log. In order to do that, I'm going to subtract 6 from both sides. Two times log base 10 of 5x is equal to 12. Next, I'm dividing 2 by both sides. Log base 10 of 5x is equal to 6. I need to convert this to exponential form. That's going to give me 10 to the power of 6 is equal to 5x. I'm going to divide both sides by 5. And now you need to type this expression into your calculator. It's going to come out to 200,000. And you should try typing that in, make sure you get the correct answer. Number 3, this one looks a little bit more complex because we need to condense these two logarithms before we can evaluate. Condensing them is going to involve the product property because I see a plus sign in the middle. This gives me log base 3 of x, and then log base 3 of x minus 24. We're going to multiply that together. So x times x minus 24 is your condensed logarithm using the product property, and this is equal to 4. We need to simplify as much as possible. This is going to, it doesn't matter at this point if you convert it to exponential or if you expand your parentheses. Either step would be acceptable. You'll still end up at the same answer. So I'm just going to expand this before I convert to exponential form, giving me log base 3 of x squared minus 24x, and this is equal to 4. Technically, this whole expression is the argument. So right now, when I convert to exponential form, because I can't do anything else, you can never separate the argument. The argument has to stay together. 3 to the power of 4 is equal to x squared minus 24x. And just a reminder from earlier in the year, anytime you're solving and you have an x squared, chances are you're going to be solving using factoring. So we need to set this equation equal to 0. 3 to the 4th is 81. So I'm going to subtract 81 from both sides. 0 is equal to x squared minus 24x minus 81. And at this point, you can factor this. This factors to x minus 27 times x plus 3. All right, this is going to give us solutions of x equals 27 or x equals negative 3. But before you can say that these are your solutions, you need to double check and make sure they do not make the argument negative. So you can have a negative value. This is what we were talking about before. Like this could be a solution, but when you substitute it back into the original expression, I drew an arrow to the wrong one. When you substitute it back into the original expression, you cannot end up with an argument that's negative. So although this could potentially work out, right away I see that it does not, because if I substitute negative 3 in for x, you're going to have a negative argument, and you do not want that. So I need to get rid of this value. If I substitute 27 in for this first one, 27 works. And then for this one, 27 minus 24 is still positive 3, so you're good on that as well. X equals 27 is your only solution. Number 4 is similar to number 3. We do have to condense this expression and then solve for the logarithm. Remember, when you're condensing, you do have to make sure your bases are the same, which they are in this case. Because we are adding, once again, this is addition, so addition is the product property. Adding will allow us to write our arguments as two multiplied expressions. Therefore, it's log base 4 of x plus 3 times 2 minus x, and this is equal to 1. I need to multiply these expressions together. Log base 4, 2x minus x squared plus 6 minus 3x. This is still equal to 1. Within this expression, I'm going to combine like terms, and I'm going to write it in standard form. Log base 4 of negative x squared minus x plus 6 is equal to 1. At this point, this whole thing is the argument. You cannot separate that anymore. So I'm going to convert to exponential form, which gives me 4 to the power of 1 is equal to negative x squared minus x plus 6. All right, we're going to have to factor because we have an x squared term. But also, if you recall your factoring process, you can never have a negative sign in front when you're factoring. So we need to eliminate that negative sign. We can either move 4 to this side and then divide everything by negative 1, or we can just move everything to this side. It doesn't matter, you're going to end up with the same answer either way. I'm actually going to move everything to this side so I don't have to show that I'm dividing by negative 1. If I do that, I have x squared plus x minus 2, and this is equal to 0. So if you're wondering what I just did there, I added x squared to both sides, I added x to both sides, and I subtracted 6 from both sides. Now I can factor this expression, and factoring that gives me x plus 2 times x minus 1. Solve for this, you have a solution of negative 2, and you have a solution of positive 1. Before we conclude that those are our solutions, we need to come back up to our original expression, or equation, and check to make sure if you substitute both of those values into these arguments that every solution comes out to be positive. Negative 2 plus 3, that's positive 1. 2 minus negative 2, that's 4. So negative 2 does work. If we substitute 1 in, 1 plus 3 is 4, and 2 minus 1 is 1. So this works as well. Therefore, both of these numbers are your solution. And this is a good example because you can clearly see that your x value is negative, it's negative 2, but it doesn't actually create a negative argument. For the next example set, we have the second type, which is where you have a log on both sides. Generally, these ones end up being a little bit faster because you're just setting the argument equal. If you have log base 5 of 4x minus 7 and log base 5 of x plus 5, if your log and the base is the same on each side, then you can just set those arguments equal. Therefore, we're going to have 4x minus 7 is equal to x plus 5. And the reason for that is those common logs are the same log on each side. In order to solve for x, we need to isolate our value of x. So subtract x from both sides, you get 3x minus 7 equals 5. Add 7 to both sides, 3x is equal to 12, or x is equal to 4. And you can check your work on this. So substitute it back in and make sure it's true. Number 2, we have log base 3 of x squared plus 3 and log base 3 of 52. Those are the same. X squared plus 3 is equal to 52. I have an x squared term, but I don't have an x term. So I can definitely use square roots on this problem if they work out. Subtracting 3 from both sides gives me x squared is equal to 49. If I take the square root, my solutions are positive and negative 7. Make sure you double check those in your original equation. Make sure that all your arguments are positive, which they are. So both of these numbers are solutions. Number 3, a little bit busier here because you have to condense the right side of the equal sign. Condensing that gives us log base 4 of x. This is going to condense using the product property because of that addition sign. So it condenses to log base 4 of 3 times x minus 2. Before I go any further, I'm going to create one single log, one single argument on the right side, giving us log base 4, 3x minus 6. Because these logs and bases are the same, you can set x equal to 3x minus 6. And x is equal to positive 3. Make sure you check your answer. It would work out here, so that is your solution. X equals 3. And number 4. Condense the left side. The bases are the same. This is subtraction. Actually, the first one we're seeing on this note sheet with subtraction. So this represents for the first time the quotient property. And the quotient property pairs subtraction with division. So I can write this as log base 6 of 4x divided by 2 is equal to log base 6 of x plus 3. Four x divided by 2 is 2x. You can divide out the common term. And once you get to this point where your log and base are the same on each side, set those arguments equal to one another. 2x is equal to x plus 3, or x is equal to 3. Make sure you check your answer, and it works in all of your arguments. It does. That is your only solution. All right, so in this box, I'll just recap this really quick. It says solving exponential equations with different bases. Sometimes we are given exponential equations with different bases. In order to solve these equations, we must know logarithms and their properties. To solve exponential equations with different bases, you're going to use logs, and you're specifically going to use log base 10. It's the common log, it's the logarithm that's in your calculator. So if you look at this memo, it says if a to the power of x is equal to b to the power of y, you clearly can't solve for that. So if that's the case, then you can write in a log in front of each term. So it kind of appears like you're just writing it in, you're just putting it in front of each value. You originally had a to the power of x is equal to b to the power of y, and then you literally just wrote this in front of it. So that's what you're doing but it's going to allow you to use your calculator to solve for the problem. If we look at an example, we have 4 to the power of x is equal to 13. We can't do anything with that with what we know up to this point. So you're going to use log base 10, which is the common log. What I'm going to do is I'm going to write that in front. I'm going to write log of 4 to the power of x is equal to log of 13. Now I have to get it to a point where I can actually type it into my calculator. Of course, I can't type x into a calculator. So what I'm going to do is I'm going to recognize that x is an exponent. I can write this in front of the logarithm. I have x times log base 10 of 4 is equal to log base 10 of 13. Now in order to get x alone and to solve for the problem, I'm going to divide log base 4 by both sides. On the left, log base 4, it should be log base 10 of 4. But log base 10 of 4 will cancel, and x is equal to what you're now going to type into your calculator, log base 10 of 13 divided by log base 10 of 4. You can see off to the right our solution is 1.85. So x is approximately 1.85. You could check that in your problem. You could type in your calculator 4 raised to the power of 1.85 and make sure it comes out to approximately 13. Number 2, 3 to the power of x minus 4 plus 2 is equal to 10. Well, we're going to check to see if we can create a common base first. You always want to check to see if you can use a common base. So I'm going to subtract 2 from both sides, and I end up with 3 to the power of x minus 4 is equal to 8. Of course, you could break 8 down to 2 cubed, but that does not give you the same base on both sides. So the only thing I can do is I can use my common log. Same thing as before, let's take this exponent, we're going to write it as a coefficient. X minus 4 times log of 3 is equal to log of 8. I'm going to divide both sides by log of 3. And at this point, I have x minus 4 is equal to log base 10 of 8 divided by log base 10 of 3. So I do need to take care of this value of 4, whether I do it now or if I do it after, doesn't matter. I'm actually going to do it now just so I only have to use the calculator once, but either way. If you're adding 4, make sure you add it to the entire expression, not just the numerator or denominator. So we have log of 8 divided by log of 3, which in my calculator I will put parentheses around, and then plus 4. And you can see off to the right, my answer is approximately 5.89. For numbers 3 and 4, I'm just going to point out that we have the number e involved with these. So anytime you have the number e, instead of using the common log in your calculator, you're going to want to use the natural log. Remember that it doesn't matter, from yesterday's lesson we learned it doesn't matter if you use the common log, log base 10, or if you use the natural log, which is just ln. Either of them is going to give you the same answer. The natural log always, for lack of a better term, we can use the natural log to undo a number e, or the number e. Okay, so number 3, e to the power of 4 minus 3x is equal to 6. Instead of writing log on both sides, we're going to just write ln, just one different key in our calculator. So ln of e to the power of 4 minus 3x is equal to ln of 6. We could rewrite this as our coefficient, 4 minus 3x multiplied by ln of e is equal to ln of 6. Now recall right here, we did this in the last lesson. ln of e is the same thing as log base e of e, and that becomes a property. So this is one more thing we're adding in here. I know it's kind of a lot, but you do have to recognize that. So log base e of e is equal to 1. And you're going to notice this on almost every problem that has a value of e. That's why you're using the natural log. I can then replace ln of e with 1. I end up with 4 minus 3x multiplied by 1. This is equal to ln of 6. We don't need to write this value of times 1. 4 minus 3x is equal to ln of 6. I'm going to add 4 to both sides. Negative 3x is equal to ln of 6 plus 4. And divide both sides by negative 3. I have to type this entire expression into my calculator. Make sure you do it in the correct order. ln of 6, which I'm probably going to put parentheses around, plus 4, and then divided by negative 3. So ln of 6 plus 4 divided by negative 3 is negative 1.93. So I made this note at the top in pink to utilize the natural log. I'm going to add to this note, and I'm going to say that ln of e is always log base e of e, which equals 1. So that leads us to number 4, which is 4 times e raised to the power of 2x plus 2 is equal to 16. Before I add or use my natural log, I can isolate this value a little bit better. I can add 2 to both sides. So I have 4 raised to the power of e, 4 times e raised to the power of 2x is equal to 18, of which I divide both sides by 4. E to the power of 2x is equal to, I'm just going to simplify this fraction. Oh, I actually realized I made a mistake. It's 16 minus 2, so it's actually 14 divided by 4, which is going to simplify to 7 over 2. Now I'm going to utilize my natural log. ln of e to the power of 2x equals ln of 7 over 2. My exponent is going to be rewritten in front. We have 2x multiplied by ln of e. This is equal to ln of 7 over 2. ln of e, you're going to replace that with 1. 2x times 1 is equal to ln of 7 over 2. And then I'm going to divide both sides by 2. And I have to type that into my calculator. My solution is 0.63. Okay, that's going to be it for today. I know there's the on your own section, but this video is already quite long. So check my answer key on my website for the on your own section answers. Just remember that when you're going through these, you have 4 different things we went over today. You have just the basic solving exponents, like the warm-up. You have the first type of solving logs, which means you only have a log on one side of the equal sign. You have the second type of solving logs, which means you have a log on each side of the equal sign. And lastly, you have those problems such as this one here, number 5, where you don't have anything in common about those 2 terms on each side of the equal sign. So you need to utilize either the common log or the natural log. All right, email me if you have any questions, and please check your answers for the on your own.